summer school. So the next speaker is Kourosh Malek from Forschungszentrum Jülich in Germany, and he will give us an overview into novel approaches in metadata management and ontologies for high-value clean energy use cases.
Thank you, Miriam. Thanks, everyone. Good afternoon. So showing hand, I want to see how many of you guys are still storing your data in your work laptop or your desktop. So you store all your data in your laptop or desktop? Most of you? Okay, so those who are not doing it, where do you store it? Which cloud? OneDrive. Okay, great. So you're not really alone in storing a lot of data in things that you don't know how you manage it or where it goes. The reality is that 55% of the data that we generate remains unused. We never use it again. And 80% of the data that is with people, it gets lost when they change position or leave. That's a problem that we are facing, not in just enterprises. We also deal with that in the research community. And probably what we deal with in research community is more severe because research community doesn't have a lot of money to redo the infrastructure, pay for consultants to do it. So we keep doing what we were doing for many years, and that's what the problem is. Okay, so I'm from Research Center Jülich. It's one of the its largest institutes within Helmholtz Society, which is the largest society in terms of research in Germany. We are located in the west of the country. We do a lot of research on a lot of different areas. We have 11 institutes, more than 7,200 people. I'm from the Institute for Energy and Climate Research. We do 80% of our research is on hydrogen and batteries, and the other research we do on the climate research as well as things related to the bioeconomy and bioenergy. I'm heading a division on the AI and data management, again dedicated to energy systems. We develop methods in data management. We develop a lot of tools, and also we develop software as well to manage different databases from different sources. So what I want to do today in this 45 minutes is that at least I want to make sure that you understand what metadata means, what ontology means, and what process we have to go through so we can make our data adapted to certain structure in terms of the metadata and ontology. We talk about a little bit about role of data in energy storage and energy transition in general. We had a lot of nice talks by my colleagues this morning about the energy systems, energy storage in particular. Maybe there was not a lot of talk about data that is generated through these systems. I emphasize on that a little bit in the beginning. And then I'm moving, talking about the fairness of the data, what that means in the first place, and what we have to do in terms of making sure our data is following that principle. Database management and ontology is something that I want to talk about in an example-based. I bring example from hydrogen industry because it's easier to talk about in terms of the process. You can relate to that process into your research. It applies to lithium-ion batteries the same way as it applies to the thermal storage or the renewables. The problem is that you might not have all the components in those technologies, and we have to work together to see if we have issue with that. And then I bring that example, and then so hopefully we have some time for discussions as well at the end. We heard a lot of problems that we have in the renewables and the energy systems, and that was, we had a lot of reasons to have energy storage. I always want to bring my own angle into this, and that's really from the consumption of electricity in the world. So by 2035, according to the usage that we had in the past 5 years, we reached to a point of 30,000 terawatt hour of the electricity. And that's a demand that is required. Just recently, because of the AI solutions that we are seeing, this number may get doubled easily. You may not know that the chat GPT that probably everybody's using is consuming more than $100 million every month to just maintain of the service. And if you add into the electric vehicles, connected softwares, we spend about 2 months to train each new events that happens in self-driving vehicles and the electric vehicles software. If you add a lot of these things happening, we have problem with the electricity consumption. And if we increase that, we have two choices. We just have to stay with the source of electricity that we have today, which is all fossil-based and non-renewable and expensive, or we have to replace them with the new sources of electricity. So if you switch to renewables, there are two other problems are coming in again. We don't have a lot of sort of continuity of these renewable sources, as you know. The intermittency of the renewables is a problem. You can only use it when you generate it. If you don't use it, you lose it, so you have to store it somewhere, and you can use it when you need it. So that's part of the storage. Greening of electricity is not always a reason or the only reason for energy storage. We also have the problem of the inflexibility of the assets, the infrastructure, and the market, as well as the old infrastructures. Big countries like Canada, as an example, is not about sort of greening of electricity. It's about infrastructure getting really old. It's extremely expensive to go and sort of renew all the infrastructure, and that's why you have to do deferral of the asset loss by applying a storage. So a storage here is important in replacing the asset as well as making sure we have enough electricity in the next little while. Something which is important, again, it came up a lot in the talks this morning, was that you don't expect, like the electric vehicles that we have, generally one technology is dominant, which is lithium-ion. In energy storage ecosystem, we don't have one technology that is dominant. We have a lot of technologies, and the reason for that is that each of these applications, let's say for deferral of the infrastructure, supporting of renewable sort of intermittency or peak shaving in the electricity grid or backup, you need different requirements, which are like performance capacity, discharge rate, or different, and that's why we don't have one single solution that works. Sometimes sort of hybridization works, sometimes different technologies working better than the other. So if you look at these graphs that you probably have seen a lot of these examples in different formats. So what I want to focus on is specifically on the hydrogen in the past couple of years. The usage of the hydrogen, of course, is important in terms of the storing of the electricity that comes from renewables. And it's very sort of versatile in terms of transferring of that of hydrogen into new fuels for running of turbines, the power electricity, and so on. The focus on the hydrogen in terms of a storage applications is more moving it from megawatt size into gigawatt size, because that's the only way that hydrogen is working into those areas of applications. And that makes sort of hydrogen as a storage extremely viable to compete with other technologies that are also viable, like lithium-ion, which is widely used in a lot of applications and so on. Okay, so hydrogen, especially green hydrogen, which is generating of the hydrogen from renewable sources, is the most expansive source of sort of energy storage in terms of its value chain. And by that, what I mean is that you can convert that into a lot of different forms of energy, like e-fuel. You can transport it for transportation purposes to industries. And no other energy storage is really able to do that all by itself. But the problem of the ambition that we have to take it from the sort of megawatt scales into hundreds of the gigawatt scale, which is the only way it makes the hydrogen economy viable in terms of the economics. We have some problems, and the main problem is the materials. Without new materials, it's almost impossible. with just engineering to go from sort of megawatt to gigawatt. So that's why a lot of focus on the hydrogen industry in general is on new materials, especially for the electrolysis. And the other thing that I want to emphasize is the acceleration of finding of these materials, which is very important. So historically, it takes about 20 years to commercialize of new materials all the way into the market. And that's really a time that a variation of that 15 to 20 years also applies to batteries and also a lot of electrochemical systems. The mass activity of electrocatalysis for fuel cell, it took 60 years to increase threefold, or or 10 to the power 3. And for electrolysis, based on same principle, we need 40 years to have 2 orders of magnitudes of improving that. And obviously, we don't have enough time to do that, right? So we have to do everything by 2035. 40 years is just not enough to do it. So the success rate also is very low. So a lot of materials that are used in the electrolysis and fuels and to a large degree on battery systems such as lithium ion is the same as it has been used forever. We have the same platinum that we were using in fuel cell in 60 years ago. For electrolysis, we have the same problem. And the thing is that the success rate of new materials are pretty low in that sense as well. Okay, so I want to focus on this problem. And then I want to tell you that the problem of this slow process is utilization of data. We do a terrible job utilizing data as a scientist, as a technician, or as a system operators. And that has to change. Otherwise, we're not able to meet any of this. And data is the core of all these accelerations that we're doing. So a fuel cell system or an electrolysis system, if you're not familiar with it, so basically it's an electrochemical system formed from the materials, the active materials. Is like electrode of the batteries. We have also same sort of active systems in the fuel cell and electrolysis. We call it catalyst or electrocatalyst. We put some polymers on top as well as some transport media, and then we coat that on a membrane. We call them CCM, catalyst coated membrane, and then we put GDL or gas diffusion layer on top, and that becomes one cell or the half cell. And then you put a lot of these things together, you have the stack of fuel cell electrolysis, and that's how you have the sort of power that you need to generate. The core problem of materials to go from sort of megawatt to gigawatt is better electrocatalyst, better engineering of the MEA or membrane electrode assembly, as well as the CCM. The process is like this. You go through a sort of a solution-based, you mix a lot of things in different pH, you find a good sort of optimum value, you coat your ink into a membrane, you have to do it in a way that is reproducible, so industry is doing it in a way that they can reproduce this in large quantities, and then you put things together, and then you have sort of MEA. So today, you're buying MEAs from the producers. So if you have commercial sort of electrolysis, that's what you do. So things that we do in the lab, if you look at a red curve, it's some improvements that we are doing in the lab only. So if you can see in the past 30 years, we have done exponential improvement of the materials and existing materials in terms of doing that in the lab. When you put that into that MEA, the same materials is not doing the same sort of efficiency as you expect. So as you can see, although sort of lab scale mass activity has gone really strong, the same materials when you put in MEA is not going as strong. And if you put in a system and a stack level, it's not really that strong. And that's the biggest problem that we have to solve. And data is really a big part of the whole thing. So to start my talk about sort of data and how we utilize that and what fairness of data means, and in that context we can use it, something which is important as a data, not scientist, as a data sort of application sort of person, you want to make sure you deal with the big data. If you don't work with the big data, fairness doesn't mean much anyway. Because the small data, it stays with people, and there is no really a specific type of sort of management needed. You talk about cloud, based storage. Person who owns the data, they know exactly how the data is stored. What we are talking about here is big data, and with the big data, there are 4 V's, as we call it. So it's a volume of the data. We're talking terabytes and millions of the data records. That's a minimum sort of size of data you're dealing with. It has the variety of the data. It's heterogeneous. So you have different data from the MEA testing to vehicle sort of data. You have data from materials all the way to sort of weather data. So it's a very heterogeneous sort of data you're dealing with. The velocity is also another impact of it, because you have different speeds of generating data and renewing of the new data. So that's also another aspect that you have to look into. And the veracity of the data is basically you're not sure if this data has a good quality or not. Is it generated by a person through some standards or not? So there's some uncertainties of the quality. If you have these 4, then you can apply some principle. And that's what we're going to talk about. So FAIR principle is, you probably have heard a lot about it, findability, sort of interoperability, reproducibility, and accessibility of data. This is a principle that has been suggested by some people in the past couple of years, has been adopted to a lot of sort of data management guidelines, but that's just the guidelines. It gives you, as principle, it gives you some ideas that, hey, I want to have, if you want to be part of my community and I respect the data that you're generating and use it, you have to adopt to this principle, which is good. Now, how to adopt to this principle is not easy. And I think that's what we have to do more and more to understand it. So that's where concepts of metadata standards and ontology are extremely important to understand how to adopt fairness of the data. And in the big picture, I told you how important it is to do it today than tomorrow, because we haven't done many of this activity in the past couple of years, and we are generating more and more data every day. And by doing so, we're just making the adoption of these things more difficult. Okay, so the relationships between the ontology, sorry, I went a little bit fast, and ontology and metadata is really here. So metadata is all about the context of your data. And when I talk about context, is that who has measured this data at what time, at what location, with what equipment, how he calculated or she calculated certain sort of factors. The context of the data is the metadata. It's basically knowledge about data, or is data about data. The ontology, on the other hand, is the relationship and the blueprint of the relationship among different data sets. Okay? If you have certain data sets that there is no relationship between them needed, you don't need ontology, right? So you already have a data from the temperature in this room versus a number of cars in the street. There's no relation, and you don't want to establish any relation, so there is no ontology needed for the system. If you have sort of relationship, which is part of FAIR principles, you always need ontologies. And in the FAIR, specifically for the findability and accessibility of the data, as well as the interoperability, ontology plays a big role. The relationship between different data sets are something that is important in this context. Okay? So you can list a few other things, metadata standards, you can read about it, some references. I'm not going through details of it. On materials level, we have done a lot of work. But what you have to also understand is that ontology is very field specific. If I define an ontology for materials for fuel cell, not exact same thing you can apply for the materials for the electrodes of the batteries. It's very similar. On a general basis, they are very similar, but you can apply the same thing. You cannot apply this for the thermal battery for that reason. You can develop same thing on the same principle, but you need a lot of insights, and you need a lot of data, and you need a lot of experts to understand it. And that's why majority of the ontologies in our field has developed is for batteries and hydrogen, not much other sort of type of storage. As part of the storage project, we do a lot of work to basically sort of harmonize a lot of these definitions. We have a long way to go, but I just wanted to emphasize on that. The other thing which is important is the data sort of management system that you're using. Data management, some of you might be familiar with sequential-based data management, right? Which is a table of data, and you put all one into one component, you call it data set. It's putting a lot of spreadsheet of Excel into one big one and call it a data set. That's a sequential based. Non-sequential, which is graph database, which I talk about it's a new way of looking at the databases, which is very specific and suitable for the ontologies, as we discussed. Okay, coming to a standard, who set the standard of ontologies? It's experts who are doing that. People who understand systems, who understand technologies, and who understand the needs. That's why, as part of the sort of materials ontologies, we have EMMO, which is European Materials Modeling Organizations, and then we have CHADA, which is for characterization data on materials. We have a good basis because these people sat together and said, this is what we have to use as a branches of the ontologies for the materials. For the other fields, let's say for aerospace, we have a good ontology. For manufacturing industry, we have a good ontology because these are Six Sigma industries that experts said that basically have very good understanding of the ontologies. In materials is just starting to become more popular. In some other fields, such as the energy storage in general, renewables, at the system level, we don't have a good ontology yet. And then we have to build it, right? So that's what the industry is going. So we're using the standard of the ontologies from EMMC, European Materials Modeling, and then we also try to sort of unify vocabulary that we use. The reason somebody has to set this is that we are not in a position to basically compare our data together if we are from different labs. So we have data lab to lab, and we have data scale to scale. Scale to scale means at the materials level all the way to the system level. Lab to lab is just different labs. If you want to communicate your data with each other, you have to have some standard. And that's how these things works. Okay, to summarize, you have a lot of data. We don't have a lot of source or the context of the data, and that's what you have to do in terms of the data itself and the metadata. In the ontology part, what you do is that you have to connect data to each other. You know exactly how data is connected. And that's really a basis of a lot of things that we're going to discuss today. So let's focus on developing such fair data infrastructure for the hydrogen technologies, specifically PEM fuel cell and water electrolysis. So first step, I take you through some steps that you have to go through to basically understand how to adopt this. The first step is that what are your data pipelines? Are they simulation data only? Are they combination of experimental data, literature data, and so on? Or they coming from robotic labs or conventional labs? The reason it's important to understand whether it's automated lab or not, because metadata is becoming very important in that sense, because if it's a robotic lab, it probably has a better sort of metadata already included. If it's conventional lab, you have to look at all the notebooks, all the data entries by human. So you have to gather a lot of data on that sense as well. And that's why this is important. Once you have that, we train our data through some sort of semantic. And by that, what I mean is that you don't want to put a human to look at all the data tables and put them in the right sort of buckets. It has to be done with an algorithm. And for one algorithm to do it, they have to understand semantic of the data. For example, if the heading of the data is potential and let's say a temperature versus the header of the data is the type of electrodes, this goes into different part of the ontology. And because we're talking big data, we're not putting human to do it. It has to be done with the algorithms that you have to sort of train to be able to do it. And all the aspects of the data, as I mentioned here, has to be there. So the first step is your data pipeline. You have to understand your data pipeline in your work. Is it just experimental data, or do I have also simulation data mixed with that? Or is it just simulation data? Is it all the data from literature I'm using for some purposes? If you have all your data, you enrich your data. Sometimes you need to enrich your data. The problem with the literature data, they are probably the most useless data for building a data structure because we don't have a lot of metadata included in it. There are few papers and publications that have every data you need to build a good metadata standard. And that's why sometimes we apply deep learning to fill those gaps based on some algorithms. If you're able to basically predict those empty points of data, we basically have to run that. Once the data is enriched, you can just get insight as it is, or use that data to train other algorithms, or do some modeling, or do some fitting, whatever you want to do with it. And then we can also generate more data, and now you have a system. And you have to make sure at that point, this structure of the pipeline is part of your workflow. You don't do it once and just put it aside and then do it again. It has to be part of how you basically do it. So practically, these things are not easy to adopt. I'll tell you how we do it at the end. The data assets, as I mentioned, it's very complex because we're talking big data and heterogeneous data. For the hydrogen systems, we're dealing with data on the fabrication of the components, the ink fabrication that has itself huge amount of the variations in terms of the conditions of the ink, pH, temperature, the type of materials, and then you have the cell fabrication, the engineering of the cell, which type of materials you use for a flow fields, and so on. And then you have also stack level. So how do you engineer a stack level and all that? So we're talking about 10,000 to 20 size million data records that we are dealing with. In an example of a stack that we do with an industry, we generate data close to 20 million in 1 month. And that's what the data is gathered. So it's a huge amount of data and very heterogeneous. So data format is important. I'll talk about it. And then these are multi-source data. I get some of that from one lab and one from the other lab. It's not easy to put them into one unless you have a good semantic in place. And building that has taken some time for us. Okay, so as an example, you can see the idea of a catalyst, CCM, which is the industrial commercialized part of the hydrogen sort of technologies, both water electrolysis and fuel cell. And there's a lot of parameters that you measure this, and also a lot of process that you have to go through. So all this data is there. The step 2 is to make your data findable and integratable ready. Either you call it AI ready or algorithmic ready. So now you have your data, it's good. You have, so hopefully a good metadata, so you have all the information of that. So if you don't have metadata, it's very hard to build a fair in the first place. So you have to make sure that you have that as much as possible. Now you have the process of the material level all the way to the device level. The data has to be findable. So how do we do it? And by findable, what I mean is that if I ask you, put all the data that you have measured at certain day or certain stack numbers in relation to this sample at certain sort of operating conditions. And I want it right now. I don't want you to go dig into your table and see where they are. And no, I want it today and I want it right now. And that's how these algorithms work. And that's where we refer to sort of findability. In most of the component level and device level, we have relationship between function of the materials and component and the properties. And then in the sort of materials level, we have the structure, characterization data with the properties. And all has to communicate really well. Okay, so one example that is showing here is that one of the best database management that we have found is basically graph databases. So I'm not going to talk a lot about basics of this. In nutshell, what we have in graph database compared to sequential databases, which as looking at the tables, is that if I ask you to find a specific data from a sequential database, which is a bunch of tables, you or the algorithm has to go and read all the tables and find the specific data that they need. With the graph database, you don't have to read all the tables. The way it is structured, you can go exactly what I'm looking for and get exact information right away. So how does it work? You will see it in an example. So one example is that one lab is using solvent, spin coating for the catalyst layer fabrication. The other lab is using heating and stirring, so a different process. If I do not have a database based on graph, I have to go and create table for this heating as a new parameter or the attributes and change all part of my sequential data. With the graph, you don't have to do it. Inherently, you can just add it into your sort of graph database and make all the relationship. It's a bit difficult to understand in that level that we're talking here. In terms of the applications, it's super fast. So you accept that from me for now. The other thing is that if you have some characterization data, metadata has to be really standardized, and that's how it really works here. For example, if you have some imaging data that is related to some part of that sort of data set, it has to go through the metadata such as the organizational data, for example, the name of the TEM sort of equipment, which lab in KIT or in Cyprus, wherever, technical data, which temperature, which conditions of sample, and all that. And that's a requirement of the data in the level of characterization. So if you want to look at some of the things we have done on the hydrogen technologies, you can look at our, let me see if I have that, just to show you. If you can go to the GitHub page that is free for use, you can see the ontologies that we have there. We have the battery ontology that is developed in part of the big map, and we put some other ontologies that is specific to the hydrogen technologies, specifically for the fuel cell and electrolysis. And as I said, they're very similar because the electrochemical systems. We're doing same thing for the solar cells, and that's how it really works. So how many more minutes I got? 10 minutes. Good. Okay, so conclusion so far is that first, your data pipeline. Second, make sure your data is findable and ready for integration. So it has to be findable, and the way to do that, we suggest graph database in this particular case. Sometimes sequential may work as well. Third step is that adopt your ontology. Most likely you don't have the ontology. If you're not in the fields that ontology is developed for, you don't know where to find it. If you're in manufacturing, sort of research or business, you have ontologies. Car manufacturing has its own ontology. The aerospace has that. Fuel cell, we have done it. For hydrogen storage and production, we have done it. For batteries, Big Map is doing that. These are really first time we're seeing these things happening. Without ontology, you have to forget about managing of research data. That's not just going to happen. And that's really something we need to pay attention to. So there are some other projects looking at the specific ontologies for the simulation data and so on, which is also very useful to look at. So the way it works is that in ontology, you have the property, process, metadata part, and so on, and the measurements. Okay? What happened? Okay, so any questions so far? No? Okay, so that's what I meant findability, how important it is. So as you can see with the graph database, that you don't have to see it really. I mean, a software that we develop, you don't have to see graph as a visual. But the thing is, if I'm looking at the process of component level, measurement is done at certain, so all these points are just one data record. I'm not showing millions of data records because you're not able to see anything. I just filtered that for you so you can see it. Is that if you can see, all the measurements are in one bucket. And all the relationships are done. So if, let's say, one of the points on the green side, we know exactly what measurements at what level is done. And for algorithms, to go and find it is pretty quick. It's very quick. It doesn't have to go to thousands of tables to find it. And you wouldn't be surprised that this is basis of everything you do in the recommendation models in Netflix or in Google and all that. These are all based on this type of database management. It's also very intrinsic, meaning if I add fabrication process, if I add manufacturing process, it's added just one layer along the pipeline. It's very easy. Okay, so that's an example of how data becomes fair and understandable at the same time findable for the algorithms. Make sure you understand that when we talk about big data, findability is not about human to find it. It's about algorithm to find it. Because you're not able to find millions of data points anyway. It's all about if I have an algorithm or the script or the query that I'm putting there, it would be able to find it right away. Okay, so not surprisingly, one of the best applications we find for these things is the self-driving labs. It's a new concept that you remove human from the labs in terms of the operating labs day to day, and we put robots there. In order to tell robots how to do the experiments and develop algorithms to suggest the next experiments, because robot is not suggesting next experiment. The scientist and human would do it. But for human to do it, it has to understand previous data and historical data or the existing data to tell what would be next. We are adopting that into some of the facilities we have in partnership in Jülich, also in Canada, as well as some other places. A good example of one of the most sort of advanced facilities are the solar cell manufacturing, pilot manufacturing that we have in Erlangen as part of our activities in Jülich. It's a fully automated system. All the experiments and improvement is done. And what they were able to achieve is that 10 times faster, they're able to generate better solar cells. Project Big Map is doing the same thing. So what you do is that you have existing knowledge, you have predictions, you have operations, and you have this data, but without a good data management process, you're not able to operate this in a day-to-day basis. What we do also in Jülich, we develop same thing for the hydrogen components, which is Jülich sort of ink optimization, or Julio. This one, we're using exact same concepts to be able to do that. So you can imagine that you're able to do thousands or tens of thousands of experiments 24/7, because a self-driving lab, it doesn't have to stop at 5 p.m. It can go as much as you want. And this data, once it's generated, is probably more quality data than what we have in the process. Okay, so all these things is difficult to do for someone who is not the data scientist or software engineer. So how do we do it? Okay, I don't expect you guys to go tomorrow and just build this. We made it easy for you by building a semantic sort of model, a language model, which is able to sort all your data in one place. We focus on the hydrogen at this point, and the reason is that we have tons of data for hydrogen, so we can train our semantic model. I cannot do it for the thermal storage unless I have millions of data for thermal storage. That same principle applies to this as well. So we have developed a software which is able to get all your data as a raw data, put that in the right ontology, and then you apply all the models you want all in one place. You just have to make sure that you always use this system as your sort of data management. Otherwise, you're losing the continuity of data. If you have imaging data, we have some transcripts that put that on the graph database, some jargons here, I don't want to go through it, but it just works seamlessly. So you don't have to worry about, as a non-expert, no-code person, you don't have to worry about data science part of it, and it just does it for you. In this platform, we're also able to accept all your models. If you have some models you want to generate and run it in your data, you can just generate your own models there. If you want to connect to experiments, if you have equipments that is able to put your data into cloud, you can do it as well. So some example of this is all here. You can see all the sort of management of data. So our dream is, at the end, I want to just talk sort of 1 minute, is that our dream is to do the entire value chain of the energy systems like this. But we are at the beginning of it. We don't have ontologies developed for the renewables, for a lot of storage technologies. I think project storage is a good start, or sort of one of the projects is looking into it. We need a long way to go to be able to do this, but that has to be the goal. And the reason we have to do this is that we don't want sort of another 40 to 60 years to improve anything. We don't have much time for that, right? So it has to happen in the 10 to 15 years. And the only way we can do it is by utilizing data in all scales, from materials to the level of the stack and systems, as well as from lab to lab. We have some workshops. If you're interested, you can participate in August, about 2-3 hours. You can use your own data and see how that works in this system. And also we have some training summer school in September as part of activities on the self-driving labs. And thank you very much.